displacement current. We have learnt in previous modules that charges in motion can exert force on a stationary magnet. Conversely, a bar magnet in motion or a changing magnetic field can exert a force on stationary charge. Maxwell suggested that a changing electric field must also give rise to a magnetic field. Let us consider the process of charging of a capacitor and apply Ampere's circuital law. Line integral around closed curve B dot dl is equal to mu naught I t. Equation 1. Let us find the magnetic field at a point P outside the parallel plate capacitor. The magnetic field is directed along the circumference of the circular loop of radius r and is the same in magnitude at all points on the loop. If B is the magnitude of magnetic field, then we have B into 2 pi r is equal to mu naught I t. Equation 2. Let us consider now a pot-like surface which has the same boundary which nowhere touches the current but has its bottom between the capacitor plates. Its mouth is the same circular loop. Now consider a tiffin box shaped surface. The surface shown does not intercept any current, as no current passes through the surface in both the cases. Therefore, the right-hand side of the equation 1 becomes 0. We thus see a contradiction. Calculating one way, we get a magnetic field B at P. Calculating another way, we find that the magnetic field at P is 0. This shows some term is missing in Ampere's circuital law. The missing term must be such that you get the same magnetic field at point P no matter what surface is used. We see that the electric field is passing through the surface S between the plates of the capacitor. If the area of plates of the capacitor is A and a total charge on it is Q, then the magnitude of the electric field E between the plates is Q upon A divided by epsilon naught. E is equal to Q upon A epsilon naught, equation 3. The electric field is perpendicular to the surface S. It has the same magnitude over the area A of the capacitor plates and becomes 0 outside it. Electric flux through the surface S. Phi E is equal to E A is equal to Q upon A epsilon naught. A is equal to Q upon epsilon naught. Equation 4. If a current I is flowing through the wire, then the charge on the capacitor plates will be time dependent. The electric flux will therefore also be time dependent. If the charge Q on the capacitor plates changes with time, then we have a current I is equal to dq by dt. The rate of change of electric flux d phi E by dt is equal to d by dt q upon epsilon naught is equal to 1 upon epsilon naught dq upon dt, equation 5. This implies epsilon naught into d phi E by dt is equal to I. Equation 6. This is the missing term in Ampere's circuital law. We know that the current due to flow of charges is called conduction current. Equation 6 shows there is also a current which is due to changing electric field or flux. It is called displacement current or Maxwell's displacement current. The generalization made by Maxwell. The source of a magnetic field is not just the conduction current, but also the time rate of change of electric field. So we can say the total current I is the sum of the conduction current, denoted by IC, and the displacement current, denoted by ID, is equal to epsilon naught into d phi E by dt. So we have I is equal to IC plus ID. Therefore, in case of charging capacitor, outside the capacitor plates, we have only conduction current. IC is equal to I and no displacement current, that is, ID is equal to 0. On the other hand, inside the capacitor, there is no conduction current, that is, IC is equal to 0, and there is only displacement current, that is, ID is equal to I. Now there is no contradiction in the value of B obtained anywhere using the generalized Ampere's law. The total current passing through any surface of which the closed loop is the perimeter is the sum of the conduction current and the displacement current. Line integral B dot dl is equal to mu naught I t is modified as line integral B dot dl is equal to mu naught I c plus I d is equal to mu naught I c plus mu naught epsilon naught d phi E by dt. The generalized law is known as Ampere Maxwell Law. By rephrasing Faraday's law of electromagnetic induction, we can say a changing magnetic field gives rise to an electric field, and an electric field changing with time gives rise to a magnetic field.